Hi guys, it's Miss Harold and I'm going to be covering a tutorial on the HR diagram. So here is just a sample HR diagram. We have our luminosity, which is also brightness or magnitude on the y-axis. And then on the x-axis, we have temperature. Okay. So it is opposite from math because in math, the x-axis increases as you go to the right. So it would be like 0, 1, 2, 3, 4, 5, all the way to whatever number. But on the HR diagram, it is reversed. So this is the low side of the HR diagram, the low temperature, and it increases as you go to the left. Okay? So 2,500 to 5,000 to 10,000 to 20,000 to 40,000. So the hottest stars are on this side, the left side of the HR diagram, and the coolest stars are on this side of the HR diagram. The HR diagram also tells us three things. It tells us the star's temperature, their brightness, and their size. Although this HR diagram is in color, make sure you know all of them are not. Let's look at the next one. This HR diagram cannot show us color. It can only show us the size, temperature, and brightness. And you can tell the size that it's on, that it is, based upon the category that it falls in. So we already know the life cycle of a star. We know that the main sequence stars are all average size stars. The giants are bigger than the main sequence. The supergiants are bigger than the giants. And the white dwarfs are very small. All right. So the HR diagram cannot tell us the color. If you forget, just remember that there are some HR diagrams that are black and white. So they all are not like this. Okay. So on Friday, we separated the HR diagram. I'm trying to get my pencil. It's not clicking on it for some reason. All right. Let's see. 1 second. Still not clicking on the pen to write. Okay, so now I think I have it working. So we separated the HR diagram into 4 quadrants. So I'm going to try my best to reenact that for you. All right, my bottom line is a little crooked, but it's okay. So all of these stars would be hot because they're on the left-hand side, and they will be bright. So I'm just going to put a B. These stars would be cool because they're on this side of the spectrum, but they would also be very bright because they're at the top. Okay. These stars would be very hot because they're on the left side, but they would also be very dim because they're at the bottom. These stars are going to be very cool, and they're also going to be very dim because they're at the bottom. All right. So remember, we learned the word dim on Friday, which means not very bright. Okay. So I'm going to erase this, and then we're going to go into applying what we know about the HR diagram to some practice questions that we should be able to answer because we have a test on Wednesday. And if you're watching this, I can let you in on a secret that you have another quiz on Monday, just to make sure we're ready for our test. All right. Come on. All right, here we go. And why will it not click to the next slide? There it is. Okay, cool. So here's another HR diagram that we have. We already looked at this. The next thing that I want to make sure that we know is our spectral class, which are these letters right here. All you have to do is find the star that it's asking about and see where it falls on the test questions. That's very simple. We did that on Friday, and I'll also do it again on Monday. All right. Here is a question that we're going to practice interpreting the HR diagram with. The HR diagram below shows how the brightness, surface temperature, and colors are related. Make sure you know that related just means how they correspond to each other. The HR diagram can only show us three things. That is brightness, surface temperature, and size. Okay? It just so happens that the surface temperature is related to the color. The hotter it is, the color changes. All right, so we have our typical HR diagram right here. Just make sure that we are able to read it. We have brightness on the y-axis, and it's going from 0 up by the thousands. Well, not by the thousands, but up to 10,000 suns, a little bit more. And this is our x-axis, and it's increasing from right to left. So you see that 3,800 is on this side and 50,000 is on this side. You got to remember that the temperature is increasing as you go to the left. Okay, let's read our question. Which of these observations of Barnard's star is most likely accurate? So first we got to find Barnard's star, and it's right here. I'm just going to color it yellow. Okay. Which of these observations of Barnard's star is most likely accurate? Barnard's star is less bright than the sun. It has a surface temperature of below 3,800 Kelvin and is red. So you have to know where the sun is to be able to answer this question. And we already know where the sun is. The sun is what type of star? What life cycle is it in? The sun is actually a main sequence star, about right here. Right here, okay. So now we're going to compare the two. Barnard's star is less bright than the sun. Is that true? Yes, that is true, because the Barnard star is lower on the HR diagram than the sun. It's below the sun, and remember, brightness is up and down. So this star is brighter than this star. This star is brighter than this star just because it's above it. So that part is true. It has a surface temperature below 3,800 Kelvin. Is that true? Well, here's 3,800 Kelvin. Barnard's star is to the right of that, means that it is actually lower. So that is true. And is Barnard's star red? Well, it's in this section right here, showing that it is red. So A is actually accurate, but let's check the others. So, answer choice B. Barnard's star is less bright than the sun. That is true. Has a surface temperature above 3,800. We already determined that the surface temperature was below, so B is incorrect. Barnard's star is brighter than the sun. We can stop right there because we know that Barnard's star is not brighter than the sun, nor is it hotter than the sun. C is incorrect, and also D. So the correct answer is A. I'm going to erase my screen and then we're going to apply it to another question. All right. Which of these correctly compares the masses of different objects in the universe? Mass is based on two things, and I hope you know what they are. So if you do, go ahead and say them. And if you don't, mass is based on, not mass, Jesus. Gravity is based on mass and distance. Okay? So it wants us to compare the mass. I don't know why I'm thinking gravity. So you have to know which object is bigger than the other object. All right? So let's read over the answer choices. A moon has less mass than a star and more mass than the planet it orbits. A planet has less mass than a galaxy and more mass than the star that it orbits. A galaxy has less mass than a moon and more mass than a planet. A star has less mass than a galaxy and more mass than a planet. So I'm going to give you a few seconds to try to decide on your answer before I explain. So I'm just going to go ahead and eliminate the ones that I know that I can eliminate. A galaxy has less mass than a moon. We know that that's not true. Galaxy has a lot more mass than a moon. And a moon does not have more mass than a planet. So we're left between G and J. The correct answer is J. A star has less mass than a galaxy, but more mass than a planet. We know that our sun can fit 1.3 million planet Earths inside of it. So the correct answer is J. So if you didn't get that correct, you need to review your components of the universe on your study buddy. All right. A Hertzsprung-Russell diagram is shown below. Now here, there's no temperature right here, but we already know temperature increases as you go from right to left. We have our luminosity, which means brightness or absolute magnitude on this side, and spectral classes at the bottom. Based on this diagram, which type of stars will belong to spectral class M and have the highest luminosity? It's all right. So our most important piece is spectral class M and the highest luminosity. I wish this line wasn't this thick. It looks like I can't change it, so whatever. All right. We're looking for a star that has to be in spectral class M, just right here. So I'm just gonna circle M. This is the spectral class that we're looking in. It also wants the one with the highest luminosity. So which stars have the highest luminosity? Is it the bottom or the top? And if you said the top, you are exactly correct. So the star at the top in this class would have the highest luminosity, and that belongs to the supergiants. So if you forgot about how to read it, I'm going to show you what some of you guys did on your quiz. On your quiz, you wrote cool on this side and you wrote hot over here so that you know. And then you wrote bright. I'm just gonna write B, well, I'll write BR for bright. And then you wrote cool down, dim, sorry, not cool. And then you wrote dim down here because any star that's at the bottom is dim. Any star that's at the top is very bright. Stars that are on the right are cool, and stars that are on the left side are very hot. All right, let me erase the screen. There's no just one click erase button, so I have to do this manually. Just give me a second. All right. 2 stars are identified on the Hertzsprung-Russell diagram below. Based on this diagram, how do the characteristics of star 1 and star 2 compare? I want you to attempt this one on your own. So I'm going to give you 1 minute and I want you to interpret it on your own. All right. Got about 10 seconds left, so let's go ahead and get our final thoughts in 5. Make our decisions in 4. All right. 3, 2, and 1. So let's look at star 1 and 2 without even looking at the answer choices if you haven't already. Star 1 is above star 2, which means star 1 is going to be brighter because it's above star 2. And it's also hotter because it's further to the left. So star 1 is brighter because it's above star 2. And I'll just put them in color. So we'll make star 1 red. And we'll make star 2 yellow. Star 1 is above star 2, higher in the graph, so it is brighter. It's at 10 to the minus 4, we'll just round up, and this one is only at 1, okay? Or not 10 to the minus 4, 10 to the 4th power, and this one is only at 1, okay? So star 1 is brighter. Now you have to look at temperature. Star 1 is further to the left, falling at about 20,000 Kelvin, while star 2 is about 7,500 Kelvin. So of course, star 1 is also going to be hotter. So the correct answer is G. Star 1 is hotter and brighter than star 2. All right, and the last one. Let me erase my marks, I forgot. All right, and let's go. The Hertzsprung-Russell diagram shows how the sun is classified among other stars, or the stars, Our sun is a main sequence star halfway through its life. So it's about 4.5 billion years old. A star that is several thousand times brighter than the sun with a temperature lower than 4,000 Kelvin will be classified as what? All right. It said several thousand times brighter. Is that going to be below the sun or above the sun? Brighter is at the top, so it's going to be above. And it says below 4,000 Kelvin, which is about right here, will be classified as what? That will be a supergiant. And here is the spectral class right here, spectral class K. So the correct answer is going to be B, a supergiant in spectral class K. Let's talk about why it can't be the other answers. A main sequence star in spectral class B. If this star was in the main sequence and in spectral class B, the temperature will be between 10,000 and 25,000, but our temperature has to be lower than this. So A is incorrect. A main sequence star in spectral class K or M. If it was a main sequence star in this direction, it wouldn't be brighter than the sun. The temperature can possibly be lower than 4,000, or it will be. However, it is not brighter than the sun because it will be below the sun on the HR diagram. Answer choice D, a white dwarf in spectral class B. Spectral class B has a temperature between 10,000 and 25,000. So that would not be correct. All right. So this concludes my HR diagram tutorial. If you have any other questions, you can message me and remind, and I will be more than happy to help you or bring your questions to class on Monday. Thanks for watching, guys.